So here's our application. It's called RS Logic 500. And so your PLC will have a little ladder symbol down here on the bottom. But before we can communicate with the PLC, we have to have the right driver. So this is one thing about Allen-Bradley's. They've been around so long, and their application supports so many different PLCs that communicate a different way. You have to specify what driver. So we have another application we call RS Links. And so this is in the RS Logic. It's in the Rockwell folder, Rockwell software, and it's called RS Links, and it's RS Links Classic. And this is what we do to communicate with the PLC. Well, first of all, we have to have the right driver. So I'm going to go to Communication, and I'm going to go Configure Driver. So we know what a driver is now, right? It's a piece of machine language program that actually controls a piece of hardware. So here's all the drivers we have available for this that communicates with Allen-Bradley's PLCs. We're going to use an RS-232 DFI, and we'll talk a little bit about that. And then once we have the driver installed, then what we have to do is configure driver. So DFI 485, it's running. I'm going to configure it. And then we got to set it up. You got to know a lot of things about it. How the baud rate, that's the speed it communicates with. Whether it's using parity, we'll talk a little bit about that. The number of stop bits, and full duplex means it can communicate both directions at the same time. Normally we just auto configure, and I must have lost it, guys. Oh, I got my PLC turned off. Let's go DA together. Okay, so it's running to its power up self-test. I gotta do the license. I'll have to do that. Okay, so it's successful. So now I should be able to communicate with the PLC. Okay. So I couldn't communicate a while ago. So we have to understand all that. If I don't know what a driver is, if I don't understand that, then I wouldn't be able. And this is the same thing that we have to do, by the way, if you're running the new application. So I would appreciate it if y'all don't play around with your cell phone and stuff in this class. If you think that's more important than listening up on my class, and you can get up and go out there, because it does affect me a lot if I think people that are not interested in what I'm saying. So please don't play games and communicate and text. You don't see me do it, so I wish you wouldn't do it in my class. And I think that's actually in the syllabus. Okay. So what is a code? Huh? It's when you use something to do what? Represent something else, right? So, like your area code. So we're 3502, 35022 here, but that's just a code that represents what? This area here that the college is located in. So we have codes that we have to understand for our computer that the computer uses, and the PLC makes available to us. Explain the decimal number system, explain scientific notation, which is very, very important. Explain exponents, learn the difference between integers, which is pretty important. integers, fractions, real numbers. RSLogic 500 calls them floating point numbers. We need to know the binary number system because this is a binary device. We'll have to be able to convert binary to decimal, decimal to binary. We're not going to have to know how to do this. I will show you how to do this in different bases, but that won't be any on any test. Explain the hexadecimal number system, convert binary to hexadecimal numbers, and vice versa. Explain the octal number system, convert binary numbers to octal, and vice versa. Explain the binary coded decimal number system and its use. Convert decimal numbers to binary code. Explain the gray code number system and its use. Explain ASCII, which is American Standard Code for Information Interchange. EBCDIC, which hadn't been around for decades. Unicode, we'll show y'all this. This is not currently used by PLCs, but it's used by everything that's on the internet. And also Microsoft Office uses Unicode. So a number written, so an exponent, this is a number written above and to the right of another number, which we call the base, that indicates the number of times the base is multiplied by itself. So this would be 8 to the 5th. So it means to come up with the actual decimal number, we would have to multiply 8 by itself 8 times. Of course, we use this so often that just about every scientific calculator has that ability, right? So here's x to the y. So I could say x, 8, and it comes up, well, good gracious. Oh, to the 5th power. So 8 raised to the 5th power comes up and gives me that. So we use this exponent so often that every scientific calculator has that feature. And you're going to use this a lot, especially in electronics and other devices. Scientific notation, a way that scientists and engineers easily handle very large and very small numbers, written as m, some number, or should be n, times 10 raised to some power. So we'd say 5.6 times 10 to the 7th power, and maybe minus 7th. And what this would do, this would tell you how many times to move the decimal point. So if it's minus, you're going to move it to the what to get the actual number, right? You're going to move it to the what? You're going to move it to the right. You're going to move it to the left, duh. And if it's positive, you're going to move it to the right if you want the actual number. Everybody okay? So if it's a minus, you're going to do what? You're going to move it to the left. If it's positive, you're going to move it to the right. As soon as I get that out. Rounding. We have a lot of problem with rounding. People think when you say rounding, it means you can just drop the fraction, and that's not true. You're going to be doing a lot of that in our classes. So a lot of our stuff, you'll come out with something that might have 15 decimal carried to 15 decimal points. So eventually we're going to have to round, right? So your instructor is going to require you to round it to 1 or 2 decimal points once you get it into correct engineer notation. So 5 or above rounds up. If it's not 5 or above, you're going to round what? Down. Everybody understand? So if I had like 6.834 and we round that to 2 decimal points, it'd be 6.83. If we had 6.835, then that would round to 6.84, right? Everybody okay? Round the number to 2 decimal points after converting to engineer notation, scientific notation. You're going to be doing a lot of this, especially in DC. We'll usually round to 2 numbers because that makes it accurate enough. Fractions. Move decimal point to the right until one whole number is reached. This is scientific notation, right? So here we would do what? We would take this number and what? And we'd stop right there. Everybody okay? And then we what? Then we round it. So 4.5. And then since this is a, since this is a 6, I'm sorry, since 6 is an 8, we would round it to a what? To a 7. And then we'd say times 10 to the minus 4th. Everybody okay? Whole numbers move to the left until we have one whole number to the left. So I'd start doing what? 1, 2, 3, 4, 5, 6, 7, 8. So 1.0. Then I would say what? What would come next? 5. And why wouldn't we round that? Because it's got a what? It's got a 3, right? Everybody understand that? Everybody okay? And then we'd say what? Times 10. And how many times did we move it? 8 times. Good. Exponents and names. So times 10 to the 0 has no names. Times 10 to the first, we call it deca. Times 10 to the second is hecta. Times 10 to the third is kila. Times 10 to the sixth, now they've jumped over some, is mega. Times 10 to the ninth is giga. And times 10 to the 12th is tera. In electronics, we're going to deal with what we call engineering notation. With engineer notation, we don't move in groups of 1, we move in groups of 3. So if I had 1,000, we'd call that 1K per kilo. And it's supposed to be a lowercase k, by the way. Over on the negative, we have deca, centa, and then we get into what you'll use in electronics. 10 to the minus third is milli, 10 to the minus 6 is micro, 10 to the minus 9th is nano, 10 to the minus 12th is pico, and that's as far as I go. In fact, we've just hit this one, 10 to the 12th, we just hit this lately. We went gigabytes for years, and now we can get disk drives that are up in the terabytes. So when we move in groups of 3s, this is called, it's a form of scientific notation, but we call it engineer notation. And what we do is it reduces what we have to learn, for one thing, but then we'll end up with some numbers that are not exactly 1 digit. So in scientific notation, we always move till we get to 1 digit. In engineer notation, we move to groups of 3s, right? You understand? So if I had 0.0125, then I go 1, 2, 3, and I would say 12.5 milli, which in scientific notation, we would have stopped at the what? We would have stopped at the 1. Engineer notation, we always move in groups of what? In groups of 3s. Everybody understand that? So this is what we're going to use. So we're not in this class technically, but in electronics, you'll use this in DC, you'll use this in intro. This is where you'll first pick up engineer notation, and you'll use it all through your studies here at the college. You can ask Corey here. He says we use it all the time. And Jalen back there in the back. The decimal number system has 10 digits running using symbols 0 through 9. So these are technically symbols. So we've learned this. So our digits that's available to us in the decimal numbering system are 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Each value that the digit holds depends on its position inside the number, right? You know, if I had 3 nines out here, each one of those are the same digit, but they hold a different weight depending on their what? Depending on their position. Everybody understand that? And the problem is that we don't really understand what's going on. Sorry, my touch screen is supposed to be turned off, so I'm going to go back. So I could have it like this, even though it looks like a bunch. They're all the same symbol. The weight they hold inside the number depends on its position, right? But y'all know that we've dealt with the decimal number system so often that you know the weight of that number right there, how much it's equal to in money or in pounds or whatever. You know it just by doing what? Just by seeing the number. Everybody okay? Base, also called the radix. Multipliers for the digits are numbers constructed of the numbering system 10 raised to some power. So this would be the base and this would be the radix. So when we come up here and write the number, this actually holds the weight of the base, which is base 10, raised to the 0 power. And any number raised to the 0 power, anybody know what that is? Do it on your... Nobody knows what that is? So let's take 9, and we'll raise it to the 0 power, and it's 1. So any number raised to the 0 power is 1. The weight of this number would be 9 times 10 to the first. The weight of this number would be 9 times 10 to the second. So 9 times 10 to the first would be 10. 9 times 10 to the second would be 100. And that's the way we learned it, right? You understand? So we didn't learn that each number holds the weight of the base raised to some power. We know that that's 999, right? We know that. We know the weight of that number. But this is the true life, the way it works. This would be 10 raised to the minus first. This would be 10 raised to the minus second. So on the opposite side of this point right here, which is technically called the radix point, but usually we give it the name by its numbering system. So we call that the decimal point, right? So numbers on the right-hand side, or this would be the same as over here. This would be 1/10. This would be 1/100. And that's the way we learn them, right? But you need to understand these powers, and this is true for any weighted numbering system. So if this was right here was a binary number, binary is base 2. This would hold a weight of 2 to the 0. This will hold a weight of 2 to the first. This holds a weight of 2 to the second. This holds a weight of 2 to the third. 2 to the fourth, 2 to the fifth, 2 to the sixth, 2 to the seventh, 2 to the eighth, right? Base 8, 3, 5, 6, 4. This would hold a weight of 8 to the 0, 8 to the first, 8 to the second, 8 to the third. Base 16, 5B, 3, 6. We'll talk about that. This would be 16 to the 0, 16 to the first, 16 to the second, 16 to the third. If I put a fraction right here, if I put a hexadecimal point, and then I wrote another number like 5, this would be 16 to the minus first. So this is the way number systems actually work, and this is why we call it base 10, because it's an exponent 10 raised to some base. If we understand this, then we can do almost any number system. So what I'm going to do